Angle bisectors. Like with perpendicular bisectors, what we will be doing is looking at this within a triangle, but before we do that, what we are going to do is just define it. An angle bisector is a ray, line, or segment that cuts an angle into two equal halves. For example, I have over here angle A, which is just any random angle. The angle bisector is going to break that in half, okay, which would roughly look like this. Okay, so I'm not going to use a protractor. What I'm going to do here is just eyeball it. Okay, so that would be an angle bisector. It will break it into two equal parts, which would mean that each of these are the same size, so that would be congruent. All right, now an angle bisector has a property to it, which is this, that any point that would be along the angle bisector is equidistant from the two sides. Okay, so if I identified a point, let's just call it P. If I identify a point P, which would be on that angle bisector, that point is going to be equidistant from the two sides. Okay, now distance is usually measured as a perpendicular, which would mean that the distance here, which I'm going to aim for that just to be perpendicular, that length of the segment here, or this segment right here, that distance would be equal to this distance right here. Okay, if they're both at a perpendicular, which is what I want in this case. Okay, so it does have that property that any point that would be on the angle bisector is equidistant from the sides. Let's go ahead and name those points of contact. Let's call this B, let's call that C. All right, so now what we're gonna do is prove that PC is congruent to PB. All right, for step one, which is usually our given information, what we have here is an angle bisector. Okay, so step one, AP, we'll go ahead and call it ray AP. Ray AP is an angle bisector. All right, and for that, we'll just write given. That's pretty much the whole set of the problem that you do have in an angle bisector. Okay, step two, if this is an angle bisector, it creates two congruent angles, which for simplicity, what I'll do is call 1 and 2. Okay, so angle 1 is congruent to angle 2 because you have an angle bisector. You have an angle bisector. All right, in step three, what I'm going to do is explain that the original picture didn't actually have these segments. Okay, so I'm going to explain that I'm adding those in there. Step three, I'm going to draw PB and PC. Okay, I'm going to draw these segments, which means I really identify point B and point C. But when I draw them, I'm going to force them to be perpendicular. Okay, I'm going to draw PB, PC, perpendicular to AB and AC. Okay, I'm going to choose to do that. All right, and that would be called auxiliary lines. All right, with those added into the picture, what we end up getting is a couple of triangles here. Okay, so my goal is going to be to prove that these two triangles are congruent. If I can prove that they're congruent, then the corresponding parts, PC and PB, would be congruent, which is ultimately what we want to get to here, that point P is equidistant from the sides. Okay, so things that I have, a couple of angles, okay, which would be 1 and 2. That perpendicular actually gives you a couple more angles. We would get that, and then we would need at least a side. The side that we could use would be AP. So step 4, AP is congruent to AP, reflexive. That'd be the reflexive property. Step 5, okay, we now got a side, and not because of the order that I have it here, but because of the order that we've got it in the picture, we do have what would be angle, angle, side. We can prove that, let's see, a triangle ABP is congruent to ACP. Those are congruent. It is going to be angle, angle, side, not because of this order here. These are actually backwards. the angles that we'd be looking at would be the right angle, that would be the angle bisector angles, and then the side, which we would have, but it does create the shortcut angle, angle, side. Step 6, we can say PB is congruent to PC because of corresponding parts of congruent triangles. All right, so that proves that any point on an angle bisector, such as P, would be equidistant from the two sides. All right, let's officially state the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant. It is equidistant from the sides of the angle. Example 1, for what value of x does P lie on the bisector of angle A? All right, so we have a picture of an angle here. That would be angle A. We also have a couple other points identified, which is B and C. Point P is just sort of out here in the middle. Okay, the question asks for what value of x? What would be the value of x that we'd plug in here such that P would be on the angle bisector? Okay, if it were on the angle bisector, we'll go ahead and just add that in there just for the sake of seeing it. So if we had that in there, if that were an angle bisector, P would have to be equidistant from the two sides. Therefore, the x plus 3 would have to equal 2x minus 1. Okay, we'll go ahead and subtract x. 3 is going to be equal to x minus 1. Go ahead and add on the 1, and 4 is equal to x. And of course, if you plug it in, you're going to get a 7 when you do 4 plus 3. You get 7, and then here, you'll get 2 times 4, which is 8, minus 1, which is also 7. All right, what we're going to do next is look at the angle bisectors of all three angles in a triangle. Okay, and when we do that, we're going to end up with a point of concurrency. We're going to get that. Okay, what we're going to start with is a random triangle. All right, every time I try and draw these, I end up with what might look like an isosceles or equilateral. Let's see if I can just get something a little bit different. All right, so I have a random triangle. Let's call this ABC, just in case we need names. All right, angle bisectors. We could use a protractor to measure and divide them up, but since I'm doing this on patty paper, what will actually work a little bit better is if I just fold over. Okay, I'm just going to fold side to side, making sure that the crease goes through an angle or a vertex. Okay, so the bottom isn't going to quite match up, but the top part is here. That will give us an angle bisector. All right, so let's highlight that. All right, that means that these are equal. These two are equal. All right, I'm going to repeat the process over here with A. Okay, fold side to side. Just make sure I go through the vertices. Get an angle bisector, which of course will cross the other one. No surprise to that. All right, but what will be interesting here is that the angle bisector C will also meet that spot. All right, we open it up and there we go. All right, we've got a point of concurrency. Then I didn't label everything, so let me go back and add these in. At A, what we could do is double markings. These will be different than the single markings over here. Over at C, we'll do triples, so that's different as well. All right, so what is interesting about this point? This point right here happens to sit on top of all the angle bisectors. And our theorem for angle bisectors is that any point, such as this point, that sits on top of an angle bisector is equidistant from the two sides of the angle that it bisects. For example, if you think of it sitting on this one, right here on that angle bisector, that means that that point is equidistant from BC as it would be from AC. It's equidistant from those two sides. But likewise, if you look at it as being on this angle bisector, it's equidistant from BC and BA. Or you could look at it on this angle bisector, which would put it equidistant from AC and AB. So it's equidistant from all the sides. What that means is that from this point, I should be able to draw a circle with a certain radius that measures out to the side so that when I measure out, I can touch all three of the sides that I have there. It's got to be equidistant from them, so the radius length out to the sides is going to be consistent. All right, let's check that out. All right, let me take a compass. All right, this might be a little bit tricky. What I want to do is avoid that point right there because that's not a perpendicular. Okay, I'm going to take a compass, measure out to the side, and I want to make sure it looks like it's just bumping into that side there. Okay, see if I can get that curve. All right, so that looks pretty good. And you'll notice it doesn't quite meet here. It's just a little bit to the side. All right, now, if I continue all the way around, you're gonna notice it makes contact just like right on the spot. It's not perfect as I did it, but it's gonna make contact right at that edge as well as over here. It does not make contact where these lines are at because it would need to be that perpendicular distance that we would have out to that spot. Okay, so that point there is going to be referred to as the incenter.
Later, blah.